is to get a nice intuitive grasp on the residue theorem and on complex functions as a whole. And as you can see, I prepared some animations that could help us in this regard. And essentially, what we will do over the next hour and a half or so is just looking at images like that and having fun with them. Of course, I will try to explain how this coincides with the residue theorem, what this has to do with the functions of a complex variable. And of course, before I switch it off, because I will need to write on the board, I can at least mention that you perhaps know some of the ways that people use to visualize complex functions, and there are many of them. But of course, it's a bit problematic because we need to plot essentially two real variables for input against two real variables for output. So in fact, we need to plot something in the four-dimensional space, and that's something that we can't really handle as humans used to the 3 dimensions. So we need to resort to tricks like using colors for one of those 3 variables, like the angle in the complex plane or something like that. And of course, this can be done, but it's kind of awkward and cumbersome because you have different information about the complex function encoded in different ways in the picture. And sometimes that's useful, sometimes it's kind of hard to grasp. But here I will offer another way of looking at the complex functions that will perhaps be more fitting, more graphic. And as you can probably guess from this kind of animation, the way of looking at the complex functions that I'm going to mention is looking at them as a vector field in a plane. So essentially, I have a 2-dimensional plane, and if I just f of something as variable z equals u plus iv, where these two things are just real functions, then I will assign to each point in the complex plane just that vector u. So for instance, I would go to this point, and here I would find out what the f in this point is, and I would just draw it. You can see that it doesn't catch it. Something like that. So I can do this for each point in the plane. And of course, once I have a vector field, then I can imagine some kind of fluid being sent in the direction of those vectors. Of course, that just corresponds to finding the integration curves for the vector field, but it's easier to visualize it just like a flow of fluid, of water or anything. And as I will show very shortly, these flows have very nice properties if it comes to the holomorphic functions, which means the functions that have the complex derivative and that have all the nice properties that the complex analysis explores. So this is essentially what we do. Now I will just get rid of population for a while. And oh, yeah, I switch it off because I don't really need it to turn the gears in the computer when you know what it's looking. Okay, so I said that it would be nice to look at the complex functions as a vector field. And of course, you will remember from the basic courses that if I have some vector field, let's say W, and now we are just talking 2 dimensions of real numbers. Let's say it will have 2 components in the Cartesian coordinates like this, and that just makes essentially the very same image. Now, of course, you know that we can calculate some things for this vector field, and one of those things is the divergence, which says how much of the fluid is going out of the particular point. So if we make the divergence of this vector field, which is just the derivative of the first component with respect to the first coordinate and the same for the second, then we get a measure of how much fluid is coming out of every single point if we just plug in the coordinates into this expression. And similarly, we can get some sense of how much the fluid is going in a vortex, like around some center. And of course, you know that this is what the curl operator is for, or rotation, as we say in Czech. And since we are in 2 dimensions, essentially the only component of the curl that will be non-zero will be the z component. So it will be pointing outside of the plane, and it will be something like dv dx minus du d. And now, when we have this, we can recall the Cauchy-Riemann conditions for the holomorphic function. So if we just consider what makes the function holomorphic after some pretty simple arguments with a complex limit and so on, we arrive to the fact that if I have such a function, and I will write it down as 2 real functions in 2 real coordinates like this, then of course for this to be holomorphic, I need to satisfy the Cauchy-Riemann equations. And those look like this. So if you have a look on that, then it will be pretty obvious that these equations are very, very similar to these 2 expressions for divergence and the curl. So if I just put everything on one side in the Cauchy-Riemann conditions, oh yes, of course. So after doing this, we will see that essentially the left-hand sides of these equations exactly coincide with these 2 expressions up to a sign. So here we have du with respect to dx plus dv with respect to dy, and here we have the same thing but with a minus. And the same thing for the curl. Here it has a minus sign, and here it has 2 pluses. So from that we can see that if a function f is holomorphic, then the vector field generated not by the function f, but by the function f complex conjugate is divergence free, because suddenly if we make the complex conjugation, the signs in the imaginary parts will flip, so we will have a plus here and a minus here, and everything will be exactly like these 2 expressions. So the complex conjugate of that function will make the divergence free and irrotational flow, which essentially means that there will be no sources, no sinks, no vortices in that flow, just everything will be some sort of perhaps normal, boring, no interesting things.
Looks like an interesting equation. Div minus 3, 0 plus a plus.
So this is some kind of nice correspondence, and of course we could use that to sway and show some more. Let's try for it. Okay, so this is the polynomial z squared plus 1. And I will get rid of some of those expressions so that you can see it more clearly. And if you try to have a good look at it, then you will perhaps be able to be convinced that it's really true that if I make any kind of a region in here, that it is true that the same amount of the fluid is coming in as it is coming out. And of course, you can see that there is no vortex or anything like that. Everything is just sort of going from left to right. And perhaps one more useful thing to notice is that if you look at these 2 points, plus I and minus I, if you look really hard, you will see that the particles that come to this point do not move at all. And that's because this polynomial has 2 roots, plus and minus I. So in those 2 points, the velocity is just a 0 vector. And because of that, the particles aren't going anywhere.
So what are you pointing to? Generating some fluid particles arbitrarily? Some random way of generating fluid particles, and then you track how they move, or
do you mean how I made this image?
Yeah.
Yeah, that's it's a bit weird, but essentially I just put a big amount of random particles into it at first, and then I just try to look up where the poles are, where the potential sources are, as I will show in a minute. And then I just add more particles into the sources, and I add them on the boundary, so more is
coming. When you move, you say when you move, you need more particles in the source because otherwise it will be empty, and at the boundary surface. Okay, but they are the dots are randomly generated snowflakes which are forced to move according to the rate.
Exactly.
Yeah. And why does this boundary appear there? I mean, it looks like it's quite a sharp.
Yeah, that's true, and that's just the effect of the crudeness of this tool. It's just essentially one day's work. And I mean, if I put greater attention to where I'm putting the particles and how many of them, then this wouldn't really.
And you put it to begin with. You put just a homogeneous.
Yeah, I just put a random.
Well, same probability everywhere.
Yeah.
And because they are not moving.
They will.
Places, then
they will just be stuck. But of course, I could just calculate where such places occur, and I could remove the particles from there, or I could add more from other directions, but it's just a very crude visualization. And this is more or less how all of the holomorphic functions look like. I could try another one. For instance, let's try. Sine error. Compile, yes, doing great. So this is a similar animation for sine of z. And of course,
you're not putting enough.
Yeah, I'm not. The problem is that I don't really know how many to put. And if they just go out in some way, I just don't track how many to replace or anything. But as you this is more boring than I thought. But if I will move a little bit, it will regenerate. So if you have a precise look, then once again you will see that there is no source in any of those regions. As much is going out as it is going. And this shows that the holomorphic functions are in some sense very boring because nothing ever happens, but we can spike it up by introducing singularities, which means points where the function is not holomorphic, and perhaps we will get some interesting effects if we just allow for these points. So as we know from our basic complex analysis course, such a singularity is made by adding terms that have some negative power of the variable. So a good thing to do would be to look at such a function, 1 over z. So let's try to do it. I will just rewrite it in such a way that I will multiply both parts of the fraction by z complex conjugate. And of course, this is the modulus. So what I now see is that if I grab this function and make a vector field which corresponds not to this function, but to the complex conjugate of this, I will get something like z over magnitude z squared. Which means that what I get is just a bunch of vectors coming out of the origin. Because the direction is always exactly away from the origin and there is just some scale. So we will have such a thing for the function 1 over z. So as we can see from this simple picture, as soon as we introduce the singularity, we can get some source. And that wasn't the case when the function wasn't allowed to have poles or any other singularities. So this is, in fact, a very nice thing to have. And as we will see, this is essentially what will make the residue theorem work. And of course, when we have this for 1 over z, then you will probably see that if I just flip the sign and make it minus 1 over z, then all the vectors will flip the sign as well, and it will be a flow into that one point, so it will be a sink. And there is one more interesting thing to do with it, and that is to multiply it with an I. If I, instead of 1 over z, grab a function that is I over z, then all those vectors will rotate 90 degrees. And so we will have to get some kind of vertex. But since we don't draw the vector field according to the function itself, but according to the complex conjugate, you will get a minus sign as well. Here, we just rewrite this, and that I will be complex conjugated as well, so we will get a minus I in the end. So if we multiply it by I, we will get a vortex, but it is a vortex that is going clockwise, not counter, of course, because we have tilted the vectors by not plus pi over 2, but minus pi over 2. So this corresponds to clockwise vertex. And we can see that after we use this, we can suddenly get some nice effects, and we can show them on the animation. For instance, let me put there this mistake. So this is the function. Went this way. So this is the function 1 over z minus 1 minus 1 over z plus 1. So, essentially, I flip this slide. Exactly. So, in this picture, we have a hole in the point minus 1, and it has a positive number in here, so that means it's going to be the C. Oh, no, it's not. I'm sorry. I'm looking at it in and the other one has a minus sign, so it is going to be C. And as you can see, all the particles are flowing inside. But of course, these 2 points are the only ones that can contribute any divergence at all. So if you look at any region that does not contain any of those points, then you can convince yourself pretty easily that it is still true that as much is going out as it is going in. So for instance, here, it just goes from right to left like in this direction, and there will be no net source of the particles. And essentially, this is the basis on which we can build the residue theorem from the physicist's point of view, because what we have now, we can pick a region, and we could calculate the flux of the particles through the boundary, and we could calculate how much of the flow goes along the boundary. That's called the circulation along the boundary. And of course, we know that if the function is homomorphic, then there is no sources, there is no vortices, there has to be nothing of it at all. And if we enclose some of the singularities, then of course we will get either a net flux or some circulation from the vortex. And the very nice thing is, and I think you can see intuitively, that no matter how the region looks like, no matter how it's shaped or how it's large or small or whatever, we will get exactly the same thing, always. Because there is just one source or anything inside that curve. And of course, no matter from how far away we look or anything like that, we are still going to get the net flow that is corresponding to contribution of that source or sink. And of course, if we drew another region that would enclose multiple singularities, something like this, then of course we would have to calculate the contributions from each of those singularities. And now we will see if I drew such singularity, it's still true that as much is going in as it is going out, because C is exactly as powerful as the source. So they sort of cancel, and the net flow is. So this is the basis of the residue theorem. And now we can just use very simple integration trick to really show it analytically. And the integration trick looks like this. So let's consider that we have some WC, which is a complex vector field. And for now, let's not assume anything about it. Let's just say that this is an arbitrary complex function. It doesn't have to be holomorphic or anything. And now let's calculate the integral of W complex conjugate dz over some curve in the complex plane. And that curve doesn't have to be closed or anything. It just should be some nice smooth curve, but I'm not expecting more of it. And let's just look at what this gives. So if I do the W complex conjugate, the imaginary part will flip the sign, and the dz, that's just dx plus I dy. So let's just multiply and separate the real part from the imaginary one. So for the real part, I have u dx minus I times another I, which makes the second minus. So we get plus v dy. And the imaginary part will be u dy. Here we get minus v dx. So if we have a careful look at it, this is something like the W dot product dr. So this term will show how much of the fluid is going along the curve. Essentially, this is the circulation along the curve. And if we look at this, this is exactly the same scalar product, but with the dr rotated by pi over 2. So this will show how much is going through the curve. So this one, the imaginary part, will correspond to the flux through the curve. So we can see that this integral is just, as we have just said, the circulation plus pi times the flux. And this result is very nice because it suddenly shows how to get all the basic results of complex analysis. For instance, if the W was holomorphic after all, then if it was holomorphic, then the W complex conjugate, as we have now shown, is irrotational and it is divergence free. So it doesn't have any sources, sinks, vortices, anything. And if we use this vector field in this formula, and if we just assume that the curve is closed, and this works for any kind of curve, then we will get that an integral over a closed curve of W complex conjugate, but there is a second complex conjugate in here. So two complex conjugate once. And of course, if I do the complex conjugation twice, it is the same thing as if I don't do it. So if I do this integral, I have to still get the same kind of thing, the circulation over the whole curve plus I times the flux. But if it was holomorphic, then it had no sources, it had no vortices. So there can't be any circulation, there can't be any flux. This has to be 0. Here you have the Cauchy theorem. If a function is holomorphic, then if you integrate over any curve that is closed, you get this. And I think you can now very easily see how this extends to the case where we have some singularity. Because this is pretty good.
Yeah, I'm thinking about one over z squared.
Yeah, I will show that very shortly what 1 over z squared. But let's now concentrate on 1 over z. And if I add such a term in here, or let's say that I add something like alpha plus I beta over z, then I get just the same kind of function that I've already investigated. And of course, if we integrate on some curve, then of course I'm going to collect the circulation and the flux from that singularity. So in the end, I will get that this is, and now we have to calculate a bit because we don't really know what the circulation and the flux is, but that's not very hard to show because we have the, if we just consider the I over z case, and we already know that it's just the same thing as IZ complex conjugate over the modulus square. And if I do the complex conjugation of this, I will get minus IZ over z squared. So the velocity has a magnitude of 1 over z. And because of that, we can see that it's the sort of ideal vortex vector field, which means that all the particles are going around with the same angular velocity. Of course, it's a bit unphysical because it would mean that the longer particles are away from the origin, the faster they will have to rotate, but it's a nice mathematical tool. And by looking at this, drawing a picture on this again. Oh, and I drew the arrows. Sorry. If I just take this kind of an integral over a circle that is centered around the singularity, then what do I find? I just have to do the scalar product like this, and since the dr of the curve is always exactly opposite to the velocity, they will just be the product of the magnitudes times a minus. So what we get is just an integral of minus r phi, and the magnitude of the velocity is 1 over r, if r is this radius of the circle, and we integrate from 0 to 2 pi. So, of course, the r cancels, and it's not very hard to evaluate this integral, we get the minus 2 pi. So, this kind of simple vortex has a circulation of minus 2 pi. And since the case with the source or sink is essentially just differing by a multiple of I in the generated function, let's say, as well as in this integral, then I don't think I need to explain really hard why the 1 over z makes a divergence of 2 pi. So now we know how much of divergence or circulation do these fields make, and we get a residue theorem, because we know that this kind of an integral needs to be equal to circulation plus I times the flux. And the circulation that is corresponding to beta is equal to 1 is minus 2 pi. So we would get minus 2 pi beta plus the flux is, of course, 2 pi times half. And we need to put an I in. And now I just can take out the 2 pi I to obtain 2 pi I times alpha plus I. So you can see that the residue theorem really works because we have recovered exactly this. And this essentially shows how the physicists can think about the residue theorem, because, of course, if we have multiple sources or vortices or anything, we just collect all the contributions, we have to sum over them. That's pretty much. So there's only one question remaining. Why did we consider the 1 over z and not 1 over z squared or 1 over z cubed or anything like that? And the answer is pretty simple. Let's do a little algebraic trick. Let's write 1 over z squared as 1 over z squared plus some a squared. And now let's send the a to the 0 in the limit. But of course, I have this polynomial here, and I can break it up into its root factors like this. And once I have broken it up, I could do the partial fraction expansion. So I could write that it's the limit a going to 0. And now let's do the partial fractions, and I won't be boring you with some lengthy derivations. I will just write it down. It should be this. Why? This, we just look at how these things add up, and we get z plus I a minus z, so the z's cancelled, but there is going to be another I a. So we have to get rid of that 2ia. And from this, we can already explain what the 1 over z squared really is. And it's a bit weird explanation, but we essentially see that it's two singularities that are very, very close to me, because we are sending a to 0. So they are really going like this, very, very close to me. And the weird thing is that as we send a to 0, of course, the power of the vortices is going to get bigger and bigger. But in the end, we essentially get two infinitely powerful vortices that are infinitely close together. Essentially, they are stacked up on each other at one point, and they sort of cancel themselves out. Because if we integrate over a curve, and there are two vortices of equal power and opposite directions, of course, we are not going to get any net circulation. So this is the reason why 1 over z squared doesn't give us anything. And of course, we could do the similar argument for higher powers.
Well, what would you do with the CPU? And then don't have equal numbers of pluses and minuses. You would have to have.
No, that's not a problem, because I could just use the complex third roots of 1.
Yeah, but here you have a source and a sink, so to speak. One is the positive, one is the negative.
Yeah, but they would be, essentially, they would have a power of 1, e to the 2 pi I over 3, and e to the minus 2 pi I over 3. And if you add up those three numbers, you get 0. So we will get three things they will be in part sources, in part vortices, but all of those powers collectively cancel. And essentially, I could write this down because I could solve this equation, then do the normal process of.
But I guess you could also
writing this.
You could split two of them and leave the third one at 0. With then maybe some other power, or some other factor or something. If I might multiply this c squared plus a squared with a z, and then do the same thing, separate out all the fractions, there would be 3 terms, 1 over z, and then this one, that. And then
you can't get anything else than z, right?
No, I'm not saying you can get anything else, I'm just saying you can do it.
Yeah, I mean that doing it in this symmetrical way is a nice way of seeing why it needs to cancel. And if you did it by putting one in 0 and the others up and down or whatever, you would get these two would have different powers from the third one, and they would have to match so that everything cancels. I think that this symmetric case is easier to convince, at least. And of course, if I derive that the 1 over z squared essentially makes two opposite vortices on one another, then of course I can even show that. So that. Oh, it's running. I'll just put 1 over z squared. Okay, so from this point of view, you can already see that it's sort of true, right? These are going like this. And we could even zoom further to have a nicer look. I think that if I do it like this, it's kind of obvious that it really is two vortices in opposite directions. And this thing, you can still see that, for instance, here the particles are coming in, but the same one is coming out. So if I just do some kind of curve around this, then I'm not going to get any circulation because there are two opposite vortices and there is the same flux in as it is.
Now you have them separated. They're not the same point. This is not 1 over z squared. This is 1 over z minus only 1 over z plus 1.
Yeah, of course, because
you could just put in 1 over z squared.
Right? No, that's what I did, right?
This is 1 over z squared, or this is 1 over?
Yeah, this is 1 over z squared.
But why do you have the rings there in different places?
But of course, yeah, then there's the artifact of this being a very crude tool, right?
Why?
There are finitely sized particles put in random places.
No, but yeah, there's a 2 rings there. What do they mean? I, or what is it? And the ring? And
oh, this is 0 and this is 0I, just a coordinate marking.
okay.
So I don't know the sources. Get rid of it.
So this is 1 over z squared.
Yeah, this is 1 over z squared. Essentially, it makes a dipole field.
Please insert there some small a,
Yeah, of course, to do that. It's, yeah. So now I will have to use a decomposition. Let's use, I don't know, 1/10, so I will get pi over I, which is this is so there is a better method of inputting the functions, so this is really so there is a experiment. And yes, of course, there is a syntax error. Oh, I know. It's one of those graphics. Sorry. Still syntax error. Oh, hard to code when I can't see what they're coding. Hopefully this is it. Oh no, I'm missing it somewhere. I'm sorry. It
looks nice.
But at least this thing is nice in the sense that it shows that we could have vortices as well.
About I always is.
I will do that. So it will get shown. Show now. Very fast. I think it's what did you say I should put in?
I obviously is there.
Yeah. It will be rotated by
So just rotate the picture.
Yeah.
Yeah, because, yeah.
It just changes the prefactor and the partial fraction.
Oh. You see, it's just. So this is essentially the way that I wanted to present how to look on the residue theorem. And by the way, one more thing: if I have a situation where there is some general complex number in the numerator of the 1 over z, like this, then I'm going to get a thing that is a vortex and the source or sink at the same. And I can show that all very easily just by this. This way. still make syntax errors even if I can see the code.
Does the computer show you?
So this is such a case. You can see that here the particles are flowing out and at the same time they are rotating. So this would be essentially the case of 1 over 2i over either z minus 1 or z plus. And of course, we could use other functions instead of these very simple fractions. And one such nice choice is using the trigonometric functions, because they are periodic, and if we divide by them, of course, they will be 0 at some places on the real line, and that will give us a whole infinite array of sinks or sources or whatever we want. So one of those functions that is particularly nice is a cotangent, and let me now show why. So we do this for a while and if I get the cotangent, and let me just use some nice scaling so that it works out nicely. But of course, if I didn't add those pi factors in there, we would just get something that would be scaled differently, but not really physically different. So if I have such a cotangent, of course, it is a ratio of a cosine and the sine. And so we can see that every time when z is a natural number, the sign is going to be 0. So there is going to be a singularity in all natural numbers. And in fact, we are going to get such an array of singularities on the real line. And now, let's just try to figure out what kind of singularities they will be. And that's not pretty hard. Just let's proceed in the usual way and do the expansion around any of those points. So let's now try to do the expansion around some, not only natural, but an integer angle. And the nice thing is that the cotangent is periodic, and the period is only pi. So if I write this, it is exactly the same thing as if I wrote pi cotangent pi z. And now, if the z is very small, it's just some small displacement from one of those poles, I just could write down the Taylor series for these two functions. So I would get pi, and here the cosine would give a 1, and then something, pi squared z squared over 2, and so on. But this is not really important, and the sine will give us pi z minus pi to the third, z to the third over 6, and so on. But if we want to calculate the residue, we are interested only in the 1 over z term. So nothing else is really interesting, and we can pull out the factor of pz to get 1 over z. And here we get just 1 minus something, blah, 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 1 minus something, blah, blah, blah. And if we are really, really close to that pole, essentially the z is going to be arbitrarily small. So here we get just a ratio of 2 1s. So we have shown that the residue at each of those points is +1. And because of that, each of those points is a source with power of 2. And that is going to be very nice for certain applications. Okay. I want to show this. So you can see it. think it's cover and file. Oh, sorry, I messed up with this. So I switch the real and imaginary parts, as you can probably see from the picture. Yeah, this is what we wanted to do. Each of those integers has a same kind of a source in it. And if we zoom away, then we will have more sources and more sources and more sources and more sources. There's an infinite amount of them on the line. And the reason why I'm showing such a function is very simple, because maybe you remember from the abstract that I promised something about some series. And of course, if I want to do some summations, which essentially means summing values of a function in natural numbers or integers, then of course it would be very nice if I could have exactly such an array of sources, because then I could just somehow mold them into whatever I want and calculate values of the different series just by summing the fluxes of all the sources.
Why is it periodic? It doesn't look periodic. I guess close to the boundary, you do treat things differently, but
Some sources are creating more particles in the left than on the right.
Well, there's still the problem with particles going from the boundary in some kind of stupid sense, because.
But still, in the middle, it also doesn't look completely periodic. On the left, they are doing more things to the left, and on the right, they're doing more things to the right. But then suddenly, everything is on the left, nothing is on the right.
I mean, this part is weird.
Yeah. Lucy has only half, missing half of that.
Yeah, I must admit that it's a bit weird. Actually, tell the reason, right?
So somehow when you're going through and putting new dots, it's discrete. So somehow because of the periodicity and the discreteness, they are not respecting somehow each other, or maybe there's some kind of rational power there.
I really don't know. It perhaps depends a bit on luck, because the particles are just put in there randomly, and of course the random swash of particles doesn't respect the periodicity.
No, but even after a while, I mean, you're choosing some points where you generate according to some algorithm. But if the one point is precisely left of a singularity, and then there's a big jump, the singularity is not in between. There's a point which is very, very close, but on the left, and then the next point is far away, but on the right. Then you're going to produce a lot of particles going on the left, and not going to the right.
Yeah, well, the problem could be that essentially I'm just making a grid,
right,
and looking for the poles.
Right.
I just put it into squares and look at each square and try to find whether there's a pole in it. But if the squares aren't well arranged, then it can happen that, I mean, there is a square and there is a pole. So if I just throw a mesh of particles in it, they will land here, they will go this way. I guess that would be the reason. I said that this tool wasn't very clever or anything. And the nice thing about the residue theorem is that if we have this, the nice thing is that the only thing that the residue theorem cares about is the strength of the individual sources or things or whatever. And it doesn't really care for anything else. So if we have this cotangent as an infinite array of sorting, then we could multiply it by pretty much anything, like this. And now we would get a different function that would have poles in all of the integers, and there would still be some sources or anything like that, but the function would multiply the power of those sources. So, for instance, if I look at the pole 0, there wouldn't be the power of 1 that is coming from this cotangent, but there would be the power of f0 times 1. And of course, in the next pole, there would be, instead of 1 from the cotangent, there would be f minus 1, and so on. So I think you can see how this will get us to summon some series, because essentially just by multiplying, we modulate the strength of these individual singularities, and the residue theorem doesn't care for anything that happens in it, because the holomorphic functions can't add any more flux or circulation or anything. So let's try out that idea, and perhaps you have already seen this weird fact that the sum of 1 over x squared equals pi squared over 6. I guess you have met that already, but now we will be able to prove not only this, but even something a little bit more general. As a little and actually a very simple example, you can do much more with this very simple idea than what I'm going to show now. So instead of that, I will try a little bit harder sum, and let's do this. Sum from minus infinity to infinity of 1 over x squared plus some constant squared. This is not very easy. Maybe it looks like it could be easy. It would be probably quite hard to do it by other methods, but here we could do it pretty easily. Why? Because we could just use the idea that we now made, and we could graph our function p cotangent pi cotangent phi z, multiply it with exactly this function, which is 1 over z squared plus a squared. And now we can consider integral of this function over some nice curve. And now we just need to figure out what a nice curve means. So let's draw the picture once again. We have a lot of poles here, and we want to, in the end, get the infinite sum. So how do we do it? Since we are just summing discrete amount of numbers, we can use a little trick. Normally, in complex integration, you try to make a nice contour that you will send to infinity in some direction, and you will hope for most of the parts of the contour to be integrated to 0. So you could actually evaluate the rest of them and get some sensible result. But here it is actually even simpler, because we don't need to send the contour to infinity in a continuous manner, we can just do discrete jumps. So, for instance, I could make squares like this. Of course, the cotangent is periodic, so if I picked wrong squares, I could get an ugly behavior from the cotangent. But if I pick nice squares, and it turns out that if I just target the squares in such a way that they pass through the zeros of the cotangent, then I will get actually a nice result. And now I won't be proving it in any formal manner, but at least let's have an intuitional look at why it works. If I start at a 0 here, then I can some sort of expect that after going in this direction, I'm not going to get really big contributions. And why? Because the cotangent in the imaginary direction is just behaving like a hyperbolic cotangent. And if I have to do it exactly, it holds that cotangent IZ is 1 over I cotangent hyperbolic Z. And the cotangent hyperbolic is a function that looks like this, for instance, e to the z plus e to the minus z over e to the z minus e over minus. So if we go to the infinity, let's say we go upwards, so that the z is positive and it's very big, then of course this e to the minus z is irrelevant, and we can just break these two. So we see that the cotangent hyperbolic goes very fast to 1 as we go to the infinity. And if we go in the other direction, then we get exactly the same thing, but this time it's going to be these two exponentials that are going to fade away very fast, and what remains are these two, so the ratio will be a -1. So as we go to the infinity, we will have just some kind of 1s and -1s in here. And here we are going from 0 in a direction where nothing really big is coming. So here we are going from 0 in a direction where we eventually expect to end up with a 1. So this is an intuitive way of seeing why these squares are a good idea. And you could just integrate over the square, break it up into the 4 parts, and do some estimations to prove it formally. I'm not going to do that. But yeah.
I'm not sure I understand. So you're integrating all the squares or just the biggest one?
I just pick one of them and I just do the limit to the infinity.
Okay, yeah. Just the biggest one.
Yeah.
Oh, okay.
I make an infinite number of squares and I do the limit of the integrals over each other.
Okay.
And of course, you could now say, wait, so I'm integrating something that is a 1, but I'm integrating it over an infinitely long line. So what about that? But the point is that we are not integrating only the cotangent, but we are integrating this factor of 1 over z squared plus something as well. So essentially, the length of this side will be something proportional to z, to the first power, and we divide it by z squared. So in the end, we are going to get something that quickly goes. And this is a thing that is nice to know, because you can't do this with any function. You need to have some guarantees that it behaves nicely at the infinitely far away points. And one way of doing this is just summing some rational functions which have the nice property of falling off at the same rate in all directions. And other functions don't have this nice property. For instance, an exponential will be falling very quickly in one direction and will be blowing up in the other direction. So we will need to make up some more tricks to handle that, and I will try to get to that as the last point of the lecture. But for now, let's use this nice idea for summing these. So if we integrate over these squares and do a limit for n going to 0, if I just number the squares by natural numbers, then what I'm going to get? I'm going to get the big integral, the big square. And now I hopefully convinced you that this is 0. And on the other hand, we could rewrite this integral using the residue theorem. And how does it work? Essentially, we catch up contributions from all of those sources that we made on the real line. So there is going to be a sum of strengths of all those sources. And as we already mentioned, the pi cotangent pi z gives sort of unit power of the flux. So we just multiply it with this 1 over z squared plus a squared, and in the end, this will have the power of 1 over a squared, this 1 over 1 squared plus a squared, and so on. So the powers of these fluxes will be exactly what I need to sum. But this is not everything, of course. If you look at this result as it is now, it wouldn't make any sense. And the reason is that we, of course, can't miss the pole that this 1 over z squared plus a squared contributes. So after all, there is one pole at some IA and another at some minus IA that is coming from this function 1 over z squared plus a squared. So we need to consider those poles as well. And that's not very hard to do because we just need.
Can you argue that this is 0? Can you just say it's an odd function?
Well, it's an even function, so
I mean, these lines, you said, well, it goes to 1 here and minus 1 here. Doesn't just follow from being odd.
I guess that works to me. Because it really is odd.
Right.
And this thing works best with even functions.
Because the way you argued, I mean, it looks a bit fishy because it looks what you wrote there is actually diverging at z equals to 0. They're hyperbolic component. So which is of course okay. So
it's not a real problem, or is it?
Well, it's 0 there. I integrating along 0. It shouldn't be 0. It shouldn't be infinite. It should be 0.
I don't understand.
On these lines, the vertical lines.
Yeah.
Those are on the zeros of the cotangent. So they are 0. Now, but then you did make this argument. Well, you're going. The z is imaginary. So then you get not a cotangent, but a hyperbolic cotangent. But that diverges on the real axis. If you just had this, it would be infinite on the real axis. Hyperbolic tangent is 0. Hyperbolic cotangent is infinite for the argument which is 0. But it's not the case, of course, because you're not at the root. It has a real part also, which is making it a bit more complicated. So it is 0, but then you wouldn't have to deal with all of this and just say it's an odd function. And
yeah,
that's it.
Still, well, the reason why I show this squares argument is that you can do something similar for functions that don't have this kind of symmetry, and you just draw the squares and do the estimates, and
Sure.
you will find out that you could just do the same thing with different functions as well that have nice properties for different kinds of sums. So that's what I wanted to show this. But yeah, it's true that doing this integral would be maybe a bit tricky because I would have to look at it from two angles or whatever. So anyway, what I wanted to do is to calculate the residues in those 2 points, and there is a little trick that you could prove if I have a simple pole and the function fz can be written as a ratio like this, and the simple pole is made up by this function being 0 at some point, then essentially you could use your normal limit argument. You are probably used to finding the residues in that way that we multiply by z minus z0, and then we send the z to the z0 in a limit, which works from the series point of view. And if we do that, we just see that psi of z, and here I get z minus 0 over phi z minus phi z0, which is 0. And you can see a definition of derivative in this if the phi in z0 is, of course, 0. So after all, I could write this as a psi of z over phi differentiated of z. And this little trick saves a lot of time when calculating the residues, so I'm going to use it, because if I differentiate this denominator, I just get 2z, and the cotangent won't have poles in this point, so I can just plug in and get phi cotangent phi IA over 2z, and plug in the IA. Then I'm going to get phi cotangent minus phi IA, and I'm going to put the minus in front. And here I will have twice the minus IA. So as you can see, there are 2 minuses, they will cancel, and here. Well, I shouldn't have wiped out the thing I am going to use right now, but the cotangent of IZ is 1 over I cotangent hyperbolic. So if I use that in here, I get that the 0 that we have in here is equal to a sum. And here, this I can go in front of the cotangent, but it will go in front with the opposite sign because of this 1 over I. So we have minus I, and that conveniently cancels with this I over here. Phi cotangent hyperbolic, because we have put that I in front over I, over A, I'm sorry. And as you can see, these 2 terms are the same, so 1/2 and 1/2 gives 1 of them. And we can cancel the i's, and now we get the sum of n squared plus a squared from minus infinity to infinity, which is equal to phi cotangent hyperbolic phi A over A. Which is not a really trivial result, and I think it's quite nice. But of course, we could manipulate this result a little bit further. Since the 1 over n squared plus a squared is an even function of n, I could break it into 3 parts. I could separate the negative terms, then just put the term with n equals 0 all by itself, and then add all the positive terms. And because this is an even function, these two sums are going to be the same. Because the square doesn't really care about the sign, so I get 1 over a squared plus 2 times sum of this thing from 1 to 0. And from that, I could just express this nicer sum that is going from 1 to infinity just by sending this 1 over a squared to the other side and dividing by 2. So after doing that manipulation, I will get that this nicer sum equals, and after putting it on the denominator, I would get this dA cotangent hyperbolic by a minus 1 over 2a squared. And of course, when I promised that I would show you that 1 over n squared summed from 1 to infinity would give pi squared over 6, I could show that very easily now because it's just sufficient to send the a to 0 in the limit. And if I do that, then the cotangent, of course, will diverge, but it is multiplied by this very convenient factor of pi a. And you could do a very simple exercise in Taylor series to show that cotangent hyperbolic of something is 1 over the something plus the something over 3 and so on. So what will happen now is that we get rid of this, we get pi a times 1 over pi a plus this term, which is pi a over 3, and so on, but we don't care, minus 1. And here, the 1 over pi a conveniently cancels with the prefactor, and the resulting 1 very conveniently cancels with this. So we have 2a squared in the denominator. And look, here is 1a and another a. They exactly cancel with the denominator, and we get the answer pi squared over 6. So we have this very beautiful and famous sum. And of course, this is just the simplest possible example. In fact, you could do much more just with this very idea. But I'm going to try and move along to the last thing I wanted to show today. And that is, what do we do if we have something more complicated?
Are you using the projector?
I think we can switch it off.
I can turn on the lights. They're not using.
Oh, yeah. Before I move on, I will just give a little remark. There are other functions you could use. For instance, if I use pi over sine pi z, that would make a similar array of poles, but they would have residues that alternate between -1 and 1. So using this would generate an infinite array of sink source, sink source, sink source, and so on. And that would be very nice if I had to calculate sums in this form. And by the way, here you can see that if you need to do some sum, then you can break it up into 2 parts, and you can, for instance, look for a good function to use as your infinite array of poles that would contribute something to the product, and a nice function to contribute the rest. So you can break it up into 2 parts and find a nice combination that in the product will give exactly what you want. And there are still other functions that you can use. For instance, a very nice thing that you can use is the digamma function. And now probably undergraduate students will be a little scared, but there's no real need for that because you have all seen the gamma function, and I know that because I taught you that, so don't dare tell me that you don't remember what the gamma function is. And if I get a logarithm of this gamma function and differentiate it, I get a function that is denoted by the letter psi, and it is called the digamma. And the nice property of this function is that it has a similar array of poles on the real line, but the poles are only on one side. So this function has singularities in 0, -1, -2, and so on, but not in the positive integers. So it would look something like that. It would be 0, and here it would be 4. So this nice function will make it possible to do some sort of one-sided sums. Here we needed to leverage the symmetry that the thing that we were summing was even, and because of that we could just break the sum into parts and extract the sum of the thing from 1 to infinity from the sum from -infinity to infinity. This function will make it very nice to extract similar values for the sums that can be only one-sided. So, for instance, one thing that I managed to do with this, and that I'm certainly going through in any way, but I think it's at least a bit amusing, is that you can do, for instance, a sum in this form. It's, as you can see, it's something quite similar to what we had before, but the square roots make our lives pretty hard. And this function, fortunately, will be very useful because the square roots are still defined only on one side of the real axis in some nice fashion. So it will be nice to have this. And using that, we could actually prove that this thing is equal to some weird integral, which looks something like this. And that's a result that the residue theorem will give you pretty quickly if you know how to look for it, and I think now you will know how to look for it. The reason why it gave an integral and not just some simple sum of residues is just because those square roots make branch points, and we need to make branch cuts.
You promise this will be 0 in the end.
Do you mean in this integral? Or? Yeah, but that's not a real problem because it isn't enough to make a divergence in there.
No, but when A is equal to B, it's the same as the sum you had before.
Yeah. But no, why? Of course, yeah, now you.
If A is equal to B, yeah,
now you need to do the limit.
It will be pi squared over 6. If A is equal to B, it should be pi squared over 6.
No, it should be this over 2a squared or b squared.
Right, if
Right, because
oh, yeah, but A is equal to B. Yeah, sure. Okay.
Then this should be 3.
You will get that from the limit. B goes to A from that integral.
Yeah, you need to.
Not 0. Oh, okay. Okay. Yeah, that's nice.
But now let's just move to the other. In the last point, I wanted to show in some detail.
Sorry, can you focus a camera? It's totally defocus. The camera. I think you need to go to the computer. Or try it, switch on and switch off. Yeah, that's better.
Yeah, is it not showing the whole view?
Yeah, it's good. It's good now. It's fine.
But we need to somehow make it more like this.
Yeah, that's okay. Thanks.
So the last thing I wanted to do is a case of sums that aren't that nice and that contain, for instance, an exponential. So a nice example of such a sum would be this. It's essentially the same thing, but now we get a weird exponential factor in here. And if we add this thing here, essentially our procedure that we used before breaks down because the exponential is decreasing very rapidly on one side of the complex plane, but it is blowing up very rapidly on the other side. So now we couldn't do such an argument with squares that go into infinity because on one side the integral would be 0, but on the other side it would diverge, so we wouldn't get anything else. And if we want to make some progress with sums like these, we need to resort to more tricks, and there is one very nice trick that leads to a famous summation formula, and I will try to show you that in the remaining time. And the trick is actually very simple. It's just a simple high school algebra at the heart of the summation formula. And the trick looks like this. Now, why that works? It's not very hard to just add up those fractions. In the denominator, we get these two multiplied together, that is 1, -1 times -1 is another one, and then we have minus e to the x minus e to the minus. In the numerator, we get the sum of these. So we get e to the minus x minus 1, and another e to the plus x minus 1. So as you can see, you get a thing that has exactly the opposite sign in the numerator, and it cancels to a -1. And this thing will be of great use, because if we need to handle sums with some sort of exponential, we could just do it in such a way that we just kill the exponential with a stronger exponential, let's say. And of course, we know that if we do e to the iz, then after writing this down as x plus iy, we get that this is e to the minus y times e to the ix. And that means that if we have such an exponential, then if we go up in the complex plane, then this y will go up, and the magnitude of this thing will decay to 0 very quickly. But the problem is that if we go to the other side, if we go down, this will blow up. But of course, we could use another exponential like this, and that would have the signs in exactly opposite places. So this exponential would be blowing up if we went up, but it would fall down very quickly if we went down. And this is the basis of the summation formula that I'm going to show, because if I have this sum, I can just grab a function and consider its integral when it is divided by some factor like this, e to the plus minus 2 pi iz minus 1. So what happens if I divide it by such a thing? Of course, the exponential is periodic, and it repeats each 2 pi I. So at each integer, this will be 1, and this whole thing will have a pole. So if we multiply the function by such fraction, we still get an infinite array of poles in some sense on the real line, and it will look pretty much the same way as it did with the cotangent. This will just have a different strength of the sources. And I will show you very quickly. But on the other hand, if we write it like this, if we use a plus sign in here, we get something that behaves very nicely if we go up in the complex plane. Because after going up, if we have the minus sign in here, this blows to infinity, and since the denominator blows up to infinity, it kills the whole fraction. So this thing is very nice in the upper half. Similarly, this thing with a plus sign is very nice in the lower half. And the only thing is how to make some use. But it's hard. Let's now imagine that I have the complex plane, here's the real line, and in every integer there is a pole of both of those functions. So I have an array of poles for this. Now I'm going to make some sort of tiles that cover the complex plane. And each of those tiles will be of a unit width, and it will go either all the way up or all the way down. So perhaps I should use the other color now. I can do, for instance, I think this would work as well, but it would be probably a little bit nicer to make the tiles like this. So on, and on the other side, exactly the same. And so on. Now, I will try to integrate one of these functions over those tiles. And let's show the order of integration. Already drawing. Now we need to pay a little bit of attention because we will go in the clockwise fashion over the tiles that are in the lower half plane. And it will shortly be clear why we do this. Let's calculate the integral of this kind of fraction over one of those tiles. Let's say that this number is kind of n, this is n plus 1 and so on, and let's go over this time, the upper one. So I will write down the integral fz over this exponential. And now let's just make out what's going on here. First, we have the 4 type of the rectangle. There's the left side, this down side, and the right side, and the upper side is somewhere in the infinity. Now, since we divided it with this exponential, we argue that this is going to infinity very fast. We could sort of expect that for nicely behaved functions, this would grow much, much faster than the function that we use. And if we are summing this kind of series, then it will happen if this x is in this range, and perhaps it's not well visible on the camera, but essentially it needs to be between -2 pi and +2 pi, because other way it would overwhelm the exponential in the denominator, then there's 2 pi as the factor. And yes, I'm cutting corners a little bit because there's not so much time left. Essentially, if I had, for instance, e to the pi I x in here, z, then if I send z to the upper half plane to infinity, then this will blow up to infinity, and this will blow up too, but it will have only half of the exponent. So essentially, this will be only square root of what we were thinking. So let's do the integrals. We have the, let's say, the left integral and the right integral. I'm not going to write them down. Then the top integral that I argued should be 0. F is sufficiently nice, so I won't be writing it down. And finally, we have this part going between n and n+1. That looks like this. I can write x just to make it clear. This is very complex. And of course, on the other hand, this integral has to be equal to some of the residues that are inside of this time. So we would get something like 2 pi I, sum of residues, and I'm not going to write it further. And now we could do very similar. I'm sorry, there's one very important thing to notice. We are integrating in a way just over this singularity. So the integration would break up if we just went right through the singularity, because the integral would be well defined. But we could do a trick and make a little circle around it. And now, if we make an infinitely small circle around the singularity, well, as we saw in the pictures, these singularities are either sources or vortices, and they are the same in all the directions. So, for instance, if I had 1 over z, and I integrated all over it in a circle or some closed curve, I would get 2 pi. But if I came really close to it and went only a quarter of a circle, then I would get just a quarter of that flux. Because this source is sending particles in the same manner in all directions. Of course, you could prove this mathematically, but I think this intuition would make it clear. So if I make a very, very small circle around this pole, I'm going to get not 2 pi I times the residue, but I'm going to get only pi over 2 times the residue, because I'm going quarter of the way, so I'm going to get quarter. So the last very important thing that needs to be here is this. I by 2 of the residue of this function in these poles. And we could do the same trick for the calculation of residue. And it will be a simple pole. We could just differentiate the denominator, and we will find that the residue is just f in the particle point over the derivative. And while we differentiate it, we get -2 pi I, and then the exponential, which gives 1, and the 1 goes away because it's a constant. So when we make it a residue, we get just the value of the function in that particular point divided by minus 2 pi I. And of course, for the other one, it would be the same thing, but it would be over plus 2 pi I, because there's plus sign. So now I could write these residues, and they are 1 over minus 2 pi I times Fn plus Fn plus 1. And now I see that I made a sign mistake in here because when we are going around the pole, we are going in the clockwise fashion. So we would integrate 2 pi I times the residue if we went counterclockwise, but now we are going in the opposite direction. So we have to fill this sign. So this is the result of integration over one of those upper tiles.
No, that's correct. Yeah. Okay.
And now we do the similar thing for the lower tiles. And I will just down. Here we have a plus sign in the exponential, and still we have the left integral and the right integral. The integral that is going to infinity will just have to be 0. We will assume that the function is sufficiently nice for that, and we add that fourth part, which will be pretty much the same, only except for the plus sign, and still we have to add up this contribution from the poles, and now we are going in the correct direction in the counterclockwise fashion, so we add up I pi over 2, then times the residue, that is Fn plus Fn plus 1 over 2 pi I. So now I may notice that these minuses cancel, and now we can do the grand finale when we just grab integrals over all of those tiles, going from minus infinity to infinity, up and down, and we add them all together. So what happens? If we look at this picture, all those left integrals and right integrals will cancel out, because in this tile, for instance, I'm going up on this side, and the very next tile is going over the very same line, but in the other direction. So when I integrate, this will cancel. This will cancel as well, and so on. So all the left and right integrals, if I extend this to the infinity on both sides, will actually cancel out with this. And if I add up these integrals that go from n to n plus 1, and I go from minus infinity to infinity, of course I'm going to get an integral that is coming all the way from minus infinity to infinity. So I will have to get rid of this ugly. Shame, it was horrible, and we space formulas. So
isn't this a way of patching? I said, why not just do the integral with this moving around the poles in the upper half plane all the way, already from the beginning?
you mean, why do I make those times?
Why do you make the patch? Okay.
Yeah,
now the only thing I can think of is that if you did that, you would still have to make the connected back at infinity, so then you would have a more complicated argument to argue that your contour is going back from not infinity to minus, then it is 0. Is that the only reason why you do?
I do that because the formula, of course, works for other cases than from minus infinity to infinity. You can, for instance, go from 0 to infinity. Really, between any two natural numbers, integers or whatever. Then, of course, you will get the sign of those. Of course, I will just make a bigger rectangle, but I think that At least for me, it just makes it sort of easier to consider each of the three tangles at a time. Probably isn't necessary for any of those cases, but at least for me, it makes it easier to understand all the possible configurations of the limits in the sum.
Well, the reason you could think that, well, you're doing this, but at some point there's the last time, and then there's not, it doesn't cancel.
Yeah, it doesn't cancel, and I actually need to say that this function will be sufficiently nice so that if I go to size to infinity, I will essentially get 0. And this is something I forgot to mention, so it's good that you bring it.
Yeah, I thought you were doing it just to not have to say that.
No, I have to say that I just forgot to say it, because I'm probably running out of time and boring it. But now we are just at the very end, so let me add up to these integrals if we do that. And I should have, I don't know if I wrote it or if I erased it. Here we have minus 2 pi I times sum of all of those residues. And why there's a minus? Because we went in the clockwise direction, in the lower half plane tiles.
But still, if you like just focus on the lower and upper half, then you make just 7/7 of the residue.
Yeah.
No? But shouldn't it be just 5x, 55x?
No. Here I talk about the residues that are not on the boundary in the real line, but somewhere else.
Oh,
so that I'm getting
yeah.
to complete. And yes, of course, I perhaps should have also said that there are no poles on the real line, because then we would have to go around them and make more exceptions and so on. So now after adding, we just get integral from minus infinity to infinity from this and from this. So here we have fx in both of them, and one of them has 1 over e to the minus 2 pi I x minus 1, and the other has the same thing but with a plus. And then we have all of these contributions, which essentially are 1/4 of value of the function at each of those poles. So in the case where the pole is inside of those limits, and this is true for all of them, we essentially get this kind of situation where the tiles go around it from all 4 sides. So after all, we just get 2 pi I here that will cancel, and we will get a sum from minus infinity to infinity of fn. And now we need to consider these residues. We just sum them all up, and now I will be more clear in writing them down, because the residues that are in the upper half plane are taken now with a plus, and they are from the function with the minus here. And the lower half plane residues will have a minus sign here, and they will have a plus sign in the exponent. So we will have this. This is the summation formula, because, as I mentioned from the beginning, there is the algebraic trick that makes this ugly bracket a -1. So essentially, we can express the sum as the integral of the same function plus some more contributions from the residues. And this very nice formula is called the Abel-Plana summation formula, although you can find various variations on this under that name, and it's quite useful if you want to study special functions, for instance, or even do sums that look like this. Now, doing this kind of sum is just a matter of plugging it into this formula and evaluating this integral using the residue theorem, which is very easily done because we just use the semicircle in the upper half, right? And I'm just running out of time horribly, so this will be the end, and I hope you enjoyed at least some of it, and perhaps you have at least some useful insight or anything out of this. So thank you for coming. That's it.
What's the result of this sum? I will have to plug f being the sum of that into that formula and calculate the rule. Like in the formula, you're plugging into what the function f, right? And the f will be the value.
Yeah, this is key.
Okay. The things you have to calculate is just the integral and the residue.
You need to calculate the residues, and the integral can be evaluated using the residue theorem. Sometimes I don't remember by heart.
There is also similar use. Lambda is using some kind of similar formula, but it's between A and B. It's not from minus infinity to infinity. I guess it would work anyway. And I don't know if you're approximating the sum with the integral, or if you're approximating the integral with the sum, and then there are some corrections.
You are essentially, if you have it between finite limits, you need to add up those integrals and go through the sides. And then you can just approximate them into some. Most often you won't be able to calculate those integrals because they will be complicated to do, but approximate them. Yeah, so program.
Here you can plug in any function into this formula. So even like the previous one, like well as well.
Well, here you must plug a function that doesn't grow too far. So we did have, for instance, such an exponential, this still needs to be big. And so if there's an exponential, the exponent needs to be between minus 2 pi z and plus 2 pi. Otherwise, this would be stronger. I mean, weaker, and it would blow up lower. And of course, you don't want to have pause on the real line, because then this wouldn't break down completely, but you would need to add another residue and so on. And it would break down this integral, because then you would need to do the breakdown.
You could go to the previous formula.
Yeah, that's something that is different.
Well, it's not. Well, it's like. Well, I think.
Yeah, that's the Euler problem, right?
Yeah. I mean, you're sort of in one case you have a sum over function, and then you're approximating it with an integral of the function plus some equation, which is very simple.
Yeah,
Totally right.
but here in fact this is exact. And here this is just a first term of plus simply something. Well, I guess I could if I try.
First derivative, this looks like a residue.